duality is to the dynamics of n equal to supersymmetric H theory, and we'll show you the marvelous things about Seiberg-Witten solution. And the lecture will be given by Stefano Cremonesi from King's College, and I am happy to give him the blackboard and the chalk. So you can start.
Thank you, Domenico. So hi everyone, I'm Stefano. You can call me Stefano, don't call me professor. I'm not professor. Don't call me doctor, even if I'm a doctor.
Don't call me professor.
Okay, so I was given this course with the enigmatic title of Rigid Extended Supersymmetry, which I took to mean 4-dimensional n equal to supersymmetry. And in particular, since this is an introductory course, let's go back to the basics. I'll actually, well, maybe I should not erase it. I take this to mean that I should explain Seiberg-Witten theory. So what I do, I'll try to introduce all the material that is needed to understand a very famous paper written by Seiberg and Witten in '94, where they were able to derive the exact low energy effective action of 4-dimensional H theories with n equal to supersymmetry. So there is plenty that could be said about 4-dimensional n equal to supersymmetric theories, both of the Lagrangian type that I will discuss here, and also the non-Lagrangian kind of theories, which have become more popular in the last few years because we started to learn many things about them. So, as I said, so there are many things that could be said, but there is limited amount of time, so I'll try just to cover the basic material. So, essentially physics as of, for the n equal to physics as of 1997 at most. But hopefully, once you understand this material, you will be able yourself to go on and read more recent papers and reviews. So I have divided the course into 4 parts of varying sizes. So in the first part, I'll talk, there will be no supersymmetry, but I will introduce some of the characters that will play an important role later on when we discuss 4-dimensional inequality theories. I will introduce monopoles, dyons, and electric magnetic duality. In the second part of the course, I will discuss basics of n equal to supersymmetry. In the third part of the talk, which is the core of the course, well, in the third part of the course, which is the core of the course, I will describe the Seiberg-Witten solution of the infrared physics of Mills theory to gauge group SC2. And in the fourth part of the course, I will describe, if I ever get there, given that we start late, I will describe some generalizations and how to derive an important object in this solution, which is called Seiberg-Witten curve, from the physics of M5 branes in M theory. So before I start, let me ask, how many people here know about Tau2A and M theory? Can I have a show of hands so I can see? All right. So, if I ever get to the fourth part, I think it will be quite pictorial. You will excuse me for that. Okay, so part 1 will be hopefully today. Part 2 tomorrow. part 3 Thursday, and part 4 Friday. Although I see that there is a tradition of running late in the school, so we'll see where we get. Okay, so I will also give a few exercises along the way that you're welcome to try and solve. I was told also that some people might want to take an exam. In that case, try and solve the exercises that will be the exam. All right, so any questions before I start? So let's start with part 1 then. Monopoles, dyons, and electromagnetic wave. Okay, so I should say that in particular in this part 1 there would be a lot to say about monopoles and dyons and so on. So I want to teach a course just on them. So I will only briefly cover some of the material that we will need later, so that the concepts that we'll use are not completely alien to you. But there are many reviews on monopoles. So for instance, if you go back to Coulomb classic lectures in the book Aspects of Symmetry, or more recent lectures like Tom lecture at Tazi or Harvey. Also on the electric magnetic duality, there are some nice lectures by Figueroa Farrell, which are available on his website. Okay, so let's start. So we start with Maxwell's equation. So the first part of this part 1 would be about abelian gauge theories, essentially electromagnetism. And later in the afternoon I will talk about non-abelian theories. So that, let's talk first about Maxwell's equation, so that we all know a lot. So they look as follows. If you write them in tensor notation. So the first equation, which contains sources, the equations of motion, are d nu f mu equal j mu, and the Bianchi identities are epsilon mu nu rho sigma d nu rho sigma equals 0, where j mu is a vector, which is a 4 vector which contains the current and the current J and the current density, so and the charge density rho. Okay, so in fact I will mostly use form notation. So the equations of motion will be d star f equals star j, where star is the Hodge dual. Everybody familiar with form notation? And the Bianchi identity is df equals 0. Okay. So let's first consider Maxwell's equations in vacuum. So where rho and j is 0, or say j mu, or j here is the current 1 form, so this is 1 form. Are 0. So then clearly this Maxwell's equation, when rho and j are 0, have a nice symmetry, which is called electric magnetic duality, which exchanges the electric field with the magnetic field and the magnetic field with minus the electric field. Okay? But if you consider charges, there are electric charges and electric currents, which break this symmetry. And so, to restore this electric-magnetic duality in the presence of sources, Dirac postulated in the 30s that there might also be magnetic currents and magnetic charge densities. Okay, so in particular, you would like to have something like d star f equals star j, but also df equals star k, where k is a magnetic current one form. And if you formally deform Maxwell's equations so that they emit magnetic currents on the right-hand side, in addition to electric currents, you restore electric-magnetic duality, and more generally, there is going to be a symmetry where you transform the vector star f and the vector j k under some linear transformation. Where M is some 2x2 matrix. Okay, so obviously, I mean, you can write these equations in vector notation, so they're invariant under this symmetry. So right now, this is just some general linear transformation. Okay. And so, however, we'll be interested in the quantum theory, and in the quantum theory, ultimately charges are quantized, and so there will be some restrictions on these matrices M that we will discuss later today. Okay. So this is the very rough overview of electromagnetic duality, but so we'll see this transformation in more detail in the rest of this first lecture. So let me first introduce notation for the rest of the course. So we follow conventions which are slightly unusual. So there are some factors of 2 and pi here and there which are different from here. I'm following some conventions in a review by Tashikawa in 2013. And these conventions, they have been chosen to simplify some of the formulas later on to avoid some factors of 2. Okay, so let me write down all the conventions and discuss electric charges, magnetic charges, and electric-magnetic duality. So let's focus on U1 gauge theory. So we'll have a gauge potential A, which is a one form, K mu dx mu, and its field strength F, which is dA of F mu dx mu. Then we have the group element. So this is a U1 group element, e to the I chi. So this is just a phase rotation, and in particular chi is going to be equivalent to chi plus 2 pi, okay? Just because the gauge group is U1. And then we're going to have a gauge transformation, which is in general A going to A plus I G minus 1 dg, which in this particular case of a abelian U1 gauge transformation is just A minus b chi. Okay. So the convention that I'll take for the curvature, the field strength of A is as follows. F is electric field EI dx naught dxi plus a half epsilon ijk d I dxj wedge dxk. So in particular, f mu would look like 0, 1, 2, 3, minus c1, minus c2, minus d3, and here b3 minus d2, c1. Okay. And then we have the Hodge dual star f, which is equal to minus bi dx naught wedge dxi plus a half epsilon ijk di dxj wedge dxk. And so this is also equal by definition of half times so star f mu dx mu wedge dx mu, where star f mu is nothing but 1/2 epsilon mu rho sigma f rho sigma. Okay. And so in particular, let me write f star f mu mu here. Still has something like 0, minus d1, minus d2, minus d3, and then here we have d3, minus d2, d1, etc. Okay, so I'm using here conventions that were epsilon 0, 1, 2, 3 with indices alpha is equal to +1. I think I differ from standard textbook conventions by some minus signs, but anyway, this we will use in the following. So next we discuss Maxwell's action. Which we take to be minus 1/2 e squared integral f wedge star f. Sorry, minus 1/2 e squared integral e for f set mu f mu. So here's this 2 is also slightly unusual. It's one of the 2 which has been written there instead of 4 to simplify some formulas. Yes.
Yeah, this is in Euclidean spacetime, right?
I'm right now I'm working in Minkowski space. So next, is there a question? So then suppose that we have a, well, okay, so next let's consider electric charge. So suppose that we have eventually some field phi of U1 charge N that we'll call electric charge. So that means that under gauge transformation governed by this group element G, phi transforms into G to the N phi, which is T to the I N chi phi. Okay. So in particular, the covariant derivative is d mu phi, which is d mu plus I, and the electric charge a mu phi will transform like g to the n mu phi covariantly. Okay. So now suppose that we want to couple an electric charge n to the gauge field. So how do we do it? So we'll introduce an action. So let's now just couple a particle of electric charge n. So we write down an action which is nothing but n, the electric charge, times a line integral of A, where L is the word line of the particle. Okay, so this is the word line. And so since in a second we're going to derive equations of motion, let me write this as an integral over the whole space as follows. So now this is an integral over the whole space-time, and delta 3 of L here is some 3 form. 3 is for 3 form. So this is in particular some closed 3 form with delta function support on the word line L. Okay. I'm just trading this integral over L for the integral over the whole space-time by inserting a delta function, and I need a 3 form here. Okay, so next we're going to see that the electric charge N is quantized. In particular, it's an integer. Well, there are several ways to see that. I guess the simplest way is that the gauge transformation is g to the n, which is e to the I n chi. But e to the I chi is a U1 group element, so chi has to be equivalent to chi plus 2 pi. So this has to be equal to the e to the I n chi plus 2 pi. Which means that e to the I n times 2 pi must be 1, so this tells us that n has to be an integer. Okay. So the other option is to Wick-rotate to Euclidean. So next we can have in the Euclidean path integral some weight, which is e to the minus s the Euclidean action for some electric charge n, and this would look like e to the, again, I n integral of A over L, the word line. So this line along L. And now if you consider closed L, closed loop, and impose gauge invariance, then you have the e to the I n integral of A over closed loop has to be equal to its gauge transform, which is e to the I n A minus dk. So this is integral equal to exponential e to the I n integral of A, and the second term is e to the minus I n times the integral of dk, which is essentially delta of k. So here k is a periodic variable chi, so in particular it can wind around this loop L a certain number of times. Okay, so but here delta k is the multiple of 2 pi. Again, because because we're considering U1 gauge rotations. And so if we want this equality to hold, this exponential factor again has to be 1, and that tells us once again that n has to be an integer. Okay. So here electric charges are quantized, and I introduce couplings in such a way that the electric charge is directly an integer, and not say an integer times a minimal electric charge. So now let's consider the equations of motion. For the electromagnetic gauge field in the presence of an electric charge. So we'll consider the action, which is a Maxwell action plus this action for a source of charge n. So this is 1 over p squared integral f wedge star f from the Maxwell term plus n integral delta 3 of L wedge A from the source term regarding to the electric charge. So if we vary this action, we find the equations of motion 2 over e squared d star f coming from this term is equal to n delta 3 of L coming from the source term. Okay, and in particular, let me rewrite it with some factors of 2 and pi introduced for later convenience as 4 pi over e squared d star f equals 2 pi n delta 3 of L. Okay, so this is the equation of motion with a source term, some delta function on the right hand side. And in particular, we can integrate this equation of motion over the hollow space to find that 2 pi n is equal to the integral over hollow space of the left-hand side, and using Stokes' theorem, this is integral of 4 pi over e squared star f on a 2-sphere, whereas here, say, we have the word line L, and the 2-sphere is a 2-sphere which surrounds or links the word line. Okay, and this is also equal to 4 pi integral 4 pi e squared electric flux of the electric field over the 2-sphere. So in particular, this also tells us, using Gauss's law, that the electric field generated by an electric charge, point like a particle with electric charge n, will look in my conventions as follows. As n times e squared over 2 times the usual r hat over 4 pi r squared. Okay? So far so good for the electric charge. Now let's discuss magnetic charges. In particular, I will discuss Dirac monopoles. Okay, so I should say that there are various degrees of sophistication in when one introduces Dirac monopoles. Essentially, the lowest level of sophistication goes back to Dirac in 1931. I will actually describe Dirac monopoles using a later formulation due to, at least in the physics community, to Wu and Yang in '75. And I should mention that there's an even deeper level of sophistication, which, for instance, you can read off in a nice paper by Argyres in '85. So, as I said, this is an increasing level of sophistication, but essentially 1, 2, and 3 is also the number of patches that you can use to describe the physics, the Dirac monopole. So, as I said, so let me follow the second explanation due to Wu and Yang. So, okay, so we want to have some magnetic charge for our electromagnetic field, and this will require some non-trivial gauge bundle. So I will try to explain how the gauge bundle, which leads to magnetic charge, can be described. Okay. So let's locate the Dirac monopole, the magnetic charge, which we take to be point-like at the origin of spatial R3. Okay, so we have our magnetic charge at the origin. So if we remove the origin, so the position of the magnetic charge, we have space is R3 minus the origin, which is contractible to S2. So essentially, its topology is the same as the topology of the two-sphere. And this two-sphere is essentially the two-sphere which surrounds the magnetic charge. Okay, and we're going to define our Dirac monopole, the magnetic charge, using some gauge field on R3 minus the origin, but essentially some gauge field on the two-sphere. And since the two-sphere is some manifold which requires at least 2 patches, we'll use the 2 patches to describe the two-sphere and write down expressions for the electromagnetic potential on 2 patches of the two-sphere. Okay, so we're going to introduce some electromagnetic potential A plus and A minus.
Sorry, which is the relation, the two relations then?
I just mean this is contractible to S2. Yes.
No, this is
Not
a different dimension. They're different.
Okay, so we want to write down the electromagnetic field, and since the two-sphere has is covered by 2 patches, we will write down the electromagnetic potential on the 2 patches of the two-sphere, and you can take it to have this form, plus and minus 1 minus cosine theta d phi, or say here we're using the usual spherical coordinates, so pick a point on the sphere, this is theta, this is phi. Okay. And so in particular, say, if you use the usual coordinate of x, y, and z, this is r sin x, r sin theta plus phi, y is r sin theta sine phi, and z is r cos theta. And in particular, if you want to write the field line, it's E1, E2, E3, say, well, now we write the field line in spherical coordinates. This is E1 is the r, E2 is r sin theta, r d theta, and E3 is r sin theta d phi. Okay, so now let's look at this expression for the gauge potential 1 form. So let's first consider A plus. So I've written A plus and A minus using the spherical coordinates theta and phi, but recall in particular that these coordinates are not well defined everywhere. So in particular, A plus is regular everywhere except at theta equals phi. which is the south pole. Okay, why is that? Because at the south pole, A plus goes like this m d phi, but the angular coordinate phi, which describes this azimuthal rotation, is not well defined at the north or the south pole. Okay. So in particular, if you use this field bind to write things which are well defined are the field binds E1, E2, E3, and this will go like say m over r theta. E3. So in particular, it diverges when theta is pi. So when theta is 0, instead everything works because we have a 1 minus cosine theta. You expand it to get the term which goes like theta squared d phi, and that's well defined. Okay? And in particular, you can go back to the original coordinates and check explicitly that A plus is well defined everywhere except for the south pole, so say the negative z axis. And similarly, A minus, where I used the other sign here, is regular everywhere except at theta equal pi, the north pole, for the same reason.
So your theta is 0.
0.
Yes.
No, the other is sure.
Like this.
Yeah.
So, okay, so we have the two patches on the sphere. So the north pole patch is defined everywhere except for the south pole. That's, well, this is something like this. So this is U plus, and then you have U minus, the south pole patch, which is defined on the other side. And we have given the gauge potential in the two different patches. So A plus is well defined on A plus, on U plus, the north pole patch, and A minus is well defined in the south pole patch. But now, since we're using two patches, we have to express how to glue the gauge field when we go from the north to south patch and when we change coordinates. Okay, so again, so A plus is defined on U plus. So this is essentially the two sphere minus south pole, and A minus is defined on U minus, which is the two sphere minus the north pole. And at the overlap, let's consider overlap of U plus intersection U minus. So in particular, we can look at the equator for simplicity. The two gauge fields, A plus and A minus, must be related by a gauge transformation. Okay. So indeed, if you look at this expression here, well, we can specialize at theta equal pi over 2, which is the equator, and we get that the difference between A plus at the equator and A minus at the equator is m, this parameter that I put here, which I'll later on identify as the magnetic charge, times d phi. Okay. And so we want this relation which expresses the gauge field potential in the north patch in terms of the gauge field potential on the south patch, this equator to be a gauge transformation. So this must be a U1 gauge transformation. Okay, which looks like, okay, so in particular here, we will conclude that G is e to the IM phi. Okay. So, all right, just by looking at this right hand side, so you say that the gauge transformation is e to the IM phi. So now, so we want the gauge transformation to be in U1. So this in particular, well, okay. So this is the gauge transformation. So now phi, again here we're working on the equator. So phi essentially is the angular coordinate here. So in particular, phi is equivalent to phi plus 2 pi. When we go around the equator by 2 pi, we're back to the same point. And so we want this gauge transformation to be single valued as phi goes to phi plus 2 pi. Otherwise, it's not well defined. Okay, and this is because the gauge transformation is e to the I m phi, and phi shifts by 2 pi. This is this gauge transformation is well defined if and only if m is an integer. Okay. So next, I'm see that I'm practically out of time. Give me 3 minutes, and I'll just finish with the magnetic charge. Oh, no, let's keep this expression here and get rid of it. So now let's compute the magnetic flux, so the integral of the form F over the 2 sphere. Well, in particular, you can use the form in local coordinates because, well, at least let's first compute it roughly using the form in local coordinates because F anyway is gauge invariant. So we get m over 2 integral sine theta d theta wedge d phi, and this integral is the area of the 2 sphere, which is 4 pi. So this is 2 pi m. And when more carefully, since everything is defined, so the gauge field of the potential are defined in 2 patches, the North Pole patch and the South Pole patch. What you would do is, if you want to compute the flux of F to a 2 sphere, you will divide the 2 sphere, say, in the northern hemisphere, and you integrate the A on the northern hemisphere. And then you would do so this with A plus, and then you would do the same with A minus on the south hemisphere. Okay? So now in the north hemisphere and the south hemisphere, we can use Stokes' theorem. So this is equal to the integral of A plus over the equator from here. And this other integral is going to be minus integral A minus at the equator. Okay, the minus sign because of the orientation. And so then this expression, we know what how A plus and A minus are related by the equator, and by using this relation, we compute indeed that this is 2 pi m. Okay. So either way, well, okay, so let me just comment that the magnetic charge m here is equal to the winding number of this U1 gauge transformation around the circle. So this gauge transformation is e to the I m phi. So as phi goes from 0 to 2 pi, it goes around the circle m times, and this winding number of the gauge transformation gives the magnetic charge. Okay, so to conclude, we see that 2 pi, the magnetic charge is integral of F on the 2 sphere, which is also the flux of the magnetic field on the 2 sphere. And so then we deduce that there is a violation of the Bianchi identity, the F, which is 2 pi m delta T of S due to a magnetic charge at the origin. So again, We have the word line, and the charge is computed by integrating the flux over a two-sphere around the word line. So in our convention for a magnetic charge M, a point like magnetic charge M, which I would call a magnetic monopole, or most often just monopole, this will generate and let's take it to be static at the origin, this will generate a magnetic field, which is 2 pi m radial unit vector by 4 pi r squared. Okay, so I will stop here for now. Are there any questions?
So geometrically, why is this happening? Is this something?
What does it mean geometrically?
I mean, is this because you've got some non-trivial holonomy on your?
Okay, so well, all right. So I wanted to describe a magnetic object, so something which would violate the Bianchi identity. So it's no longer true that the F is 0. So in particular, I cannot introduce a gauge potential everywhere because the F is non-zero. But so what I'm going to do, what I've done is to consider the space outside the source, and this was say R3 minus the origin. There is no source. The gauge potential can be defined because the Bianchi identity, the F equals 0, is satisfied. But the price is that to describe R3 minus 0, I need two patches. And so the gauge bundle, so one usually says that the gauge bundle is non-trivial because you have some non-trivial gauge transformation that tells you how to patch the gauge field in, how to glue the gauge field in one patch to the gauge field in the other patch. And it's this non-trivial gluing condition which gives rise to magnetic charge. In the original description by Dirac, he didn't use two patches, but then he introduced the so-called Dirac strings. Essentially, he was only using the gauge field at A+. This is not defined at negative Z, and was introducing some unphysical Dirac string, which is essentially a solenoid which cancels the singularity. But and then by demanding that this auxiliary Dirac string was unphysical, so the Aronoff-Bohm phase is, as you go around it, is 0 or multiple of 2 pi to derive magnetic charge quantization. But I mean, in modern language, there is no just. You probably shouldn't think of Dirac string. It's just that you're working on R3 minus the origin, and you need at least two patches to cover R3 minus the origin. And so you have to express how the quantities, and particularly the gauge field in one patch, are related to the gauge field in the other patch, and have to be related by U1 gauge transformation. Okay, so let me just comment that so this is all good and correct for the two-sphere, but in fact, in general, one has to be a bit more careful. You need to work with at least 3 patches, and okay, you can still deduce the same magnetic charge quantization, and I refer you to this article by Argyres. I can dig up the precise reference for a description of that approach. Okay, any other questions? Okay, so I'll see you this afternoon.